I worked before like 3 years as structural engineer, and I was responsible for seismic modeling actually, and like seismic design. To begin with, we all know the famous equation for the base shear is CS multiplied with W. This is the equation we see before in our classes, and the doctor described it before. So the W is the seismic weight, and it's usually the dead load. And in some case, we add 25% of the live load. The ASCE code said in the area used for storage, a minimum of 25% of the floor live load shall be included. So we don't have problem with the effective weight, but the CS, this term is different actually from code to code. And in this session, we will describe it from the ASCII code. And as we can see, CS is the seismic response coefficient. And this is the relationship for the CS. It's SDS over R over IE. This seismic coefficient have an upper limit and have a lower limit. So the maximum value for CS should not exceed CS equal to Sd1 over T multiplied with R over IE. This is for T less than T large, and in case of T more than T large, we have another equation. But usually all of normal structure is located in this part. So we will concentrate on this. And the minimum value for CS that should be not less than 0.044 multiply SDS multiply IE. Okay, to understand this equation, we should understand what is SDS and what is SD1, what is T, what is R, what is IE. So we will begin first with SD1 and SDS. Actually, to calculate SD1 and SDS, we should have at beginning S1 and SS. This value usually given by code, and it's related to where we study the structure. So Malaysia will have different values than America, than other part of the world. So this is a given value. And in order to have SD1 and SDS, we have go through some calculation to be able to calculate it. So what is S1 and SS? S1 is spectral response acceleration for the maximum considered earthquake with 5% damp at a period for 1 second for site class PC. And SS is also spectral response acceleration parameter for maximum considered earthquake for 5% damp at a period of 0.2 seconds for site class PC. To begin with, we should concentrate on many things related to these parameters, these parameters for maximum considered earthquake. I will describe more about this, but let's also see what we have. We have the difference between SS and S1 is one for period of 1 second and one for period of 0.2 seconds. Actually, this is called short period also, and it's for site class BC. So these values are obtained for specific type of soil. And actually in our structure, maybe we will have a different soil type. Maybe it will be C, D. We will also see it later, how we can classify the soil. So we will compute SM1 and SMS. SM1 and let's say about SM1 is spectral response acceleration parameter at a period of 1 second adjusted for site class effect. So basically S1 is same as SM1, but it's multiplied with same value to make it for our site class. And SMS is same as SS, but it's edited for the site class that we have. So we see in the equation SD1 and SDS. SD1 and SDS is the spectral response acceleration at period of 1 second for design earthquake. So we will compute SD1 from SM1 and SDS from SMS. To better understand this, I will talk a little bit about maximum considered earthquake and design-based earthquake. The maximum considered earthquake is the ground shaking level at the building with a 2% probability of exceedance in 50 years. So This earthquake will happen. The chance of happen of this earthquake is only 2% in 50 years. But we usually don't design for this. We design for design-based earthquake, the ground shaking level at the building site with 10% probability of exceedance in 50 years. So we designed for this value, and this value is assumed to be 2/3 of MCE. So as we can see, this is a chart for the response spectrum for the MCE and for the DBE. This is the value of the MCE, and this is the value of DBE. Let me have. Okay, this is the value of the MCE, and this is the value of DBE. And usually we design for DBE. It's more economical. And as we see, like there is a chance that maybe in real life there will happen earthquake that exceed of this earthquake. And this is actually make interesting, make this field interesting, because sometimes we should structural engineer should be able to understand more that the code is giving the minimum requirement. Not in usually when we design in static, we have the maximum, like we take the critical case, but in the case of seismic design, it's not always this case. So now we understand what MCE and DBE. DBE will be 2/3 of the MCE. So yeah, so we will have Sd1 and Sds as 2/3 of the SM1 and SMS. So how we calculate SM1? We said SM1 is same as S1, but it's edited for the soil. As we can see on this graph also, we have spectral acceleration for different site class. It's same earthquake, but it's different sites. Like usually the codes give for B, and we see maybe we have soil type C, so we will amplify this. And this is actually a very important factor. It's usually given by geotechnical engineer, and with the geotechnical report, what is the soil type class, but we also learn how to know what our soil type. So we have FV and FA. It's given by table 1142 and 1141 for specific site. It's related. We know now what S1 and SS and site class, our site class, and we can compute the value. And then we have SD1 and SDS. SD1 is 2/3, as we said before, of SM1, and SDS is 2/3 of SMS. So this is how we compute SD1 and SDS. Now, what is R? R is response modification coefficient. It's given by table 12-1, and it's related to seismic force resisting system. So in case of bearing wall, we'll have different values than moment resisting frame. Actually, we have 5 main systems. It's bearing wall system, building frame system, moment resisting frame system, and 2 kinds of dual system. And it's related to material actually. So this coefficient actually take the account of the nonlinearity of the structure, because as I said before, we don't design for elastic structure. We allow some damages, and equivalent lateral force is considered a linear method. So how we will take account the nonlinearity of the materials and of the structure, it's by this coefficient. So let's say if maybe have a special reinforcement concrete moment frame, we will have a response modification coefficient as 8. So now we know SD1 and R and SDS. Let's talk about IE. IE is seismic importance factor. And before we could compute IE, we should know the risk category of our building. We can obtain the risk category of the building from table 1.51. And usually most of the buildings are located in this, in the risk category 2. Maybe hospitals will locate it at 4. Sometimes high-rise building will locate it at 3. So after we choose what the risk category, we go to compute the importance factor, and it's easy process actually. because here we have maybe 2, and it will be 1. So it's only amplification factor in case of very important structure. Now we know what SD1 and what SDS and what R and what IE. So the last parameter to consider is T. What is T? Actually, T is, we know this value. It's a parameters referred to the fundamental period of structure. In the dynamic classes, we know what T is and how to calculate T. But here we should differentiate between many things, because we usually apply the seismic force in 2 independent directions. Like we will have a seismic force applied for the X direction, and independently, we will have one in the Y direction. So we will have period for the X direction, and we will have period for the Y direction. And in the same direction, we also have 2 periods. One period is compute from the model that you will model your structure and do model analysis, and it will give you a period, this period from model analysis, and one given by the code. The one is called approximate fundamental period. This approximate fundamental period is have the following equation: TA equals to CT multiplied with HN power of X. HN is the height structure, and CT and X is related to the structural system that we use. So from table 12A2, we can see the value of the CT and X. Actually, this is 2 values that used for concrete. The other one is for steel. So the concrete moment resisting frame will have this value in meter, and this is in feet. And this is same for meter and feet. So we will have the concrete moment resisting frame, and maybe shear wall structure will have these values, or all other type of structures, the concrete structures. So we have 2 periods. Which one we should select? Actually, this is by the ASCE, the fundamental period T should not exceed the product of the coefficient for upper limit calculated period CU from table 12.8.1 and the approximate fundamental period TA. What does this mean? We have one T from the model, as we said, and we have this TA that compute from this. This one should multiply with another value, it's CU, and CU actually is given by this table. It's related to SD1. We calculate SD1 before, and maybe if we have SD1 0.2, we'll have CU 1.5. So the T that we will use, it will be minimum between the T from model and TA multiplied with CU. The minimum of this value we will use in the equation. So now we know all these parameters, but how we do this in real life, or how we do it on ETABS? Actually, this steps is followed in real life and in ETABS, and this is how we work usually. First thing to do, we have approximately 8 steps. The first step is determine risk category of the building, and the second step importance factor, third step SS and S1, fourth step site classification, 5th step SD1 and SDS, and the 6th step is seismic design category, 7th step response modification factor, deflection amplification and overstrength, and the 8th step is period determination. Okay, for this example, we will use a model. It consists of 5-story buildings. It's residential buildings. The height of the ground floor is 3.5 meters. The other floor height is 3 meters. So the total height is 15.5 meters. In the X direction, we will have 5 spans over 4 meters, and in Y direction, 3 spans over 4 meters. We will have dead load as 5 kilonewton per meter square, and live load 3 kilonewton per meter square, and the average shear wave velocity 2,000 feet per second. This model is modeled already on ETABS, and we neglect the self-weight for the components in order to have verification with the manual calculation. So the first, we have this model. We model the model, how we will apply the seismic law. But first, we have some steps that we should do it manually before we start to go into program immediately. First, we determine risk category of the buildings. As we said before, most of the buildings located in the second category, it's this from table 1.51. And our structure will locate it to its residential or commercial residential building into, and usually normal commercial building also into. So it's category 2. Then the importance factor, as we said, from table 1.52, we will go for risk category. Our risk category is 2. So this is seismic importance factor, it's 1. So IE is 1. Now, SS and S1. Actually, SS and S1 given in the ASCII code, it's related to USA. So like if you are doing building in Malaysia, you cannot use this. In this example, I will use one that from Dubai, United Emirates, and it's given by the Emirates code, actually, the SS and the S1 for Dubai. So the SS and the S1 for Dubai is given by the code is 0.51 for SS and 0.18 for S1, and TLR is 24 seconds. And we should notice actually what the site class that it's given. Because sometimes when we do seismic hazard analysis for the in the location of the structure, maybe it will given for our site class. So we go directly to the design one. So we should not notice what site class is giving. This is giving for site class B. So we should calculate SMS and SM1, and then SDS and SD1. But before we do that, we should know what site classification. The site classification, as we see.
Sorry, Amr. Let me here put some comments for our friends. Okay. Because yeah, in the session 2 of our class, we were talking about the ASCE 722. As you can see here, our friend Amr is talking about the ASCE 716. Okay, so which means the older version of current ASCE 722. Okay, and that's why here actually you can see the SS, S1, Sd1, SDS, and we call it this kind of let's say design spectral acceleration. So we call it as 2-point design spectrum acceleration curve. Okay, which is actually based on SS and S1. So in ASCE 722, actually this 2-point design spectrum acceleration is not longer used in in the new code, and the new design spectrum uses 22 points, and it is a smooth curve. So it means that no more plateau region that occurs in the 2-point method. Okay, so that's why in ASCE 722, so you cannot find the SS or S1, and also later Amr will talk about the FA and FV factor as well. Okay, so which is related to actually the swell type class, and those factor also you cannot find it in ASCE 722. So where you can find those values if you want to use the ASCE 722. So actually you need to use the free online ASCE 7 hazard tool. If you remember in the second class, so I showed you actually how you can use the ASCE hazard tool. Okay, so you can go to the ASCE website and also go to the hazard tool option that you have, and simply you can key in the value, the seismic parameters, and let's say the site class, the risk category. So all those parameters can be inserted in the online ASCE hazard tool platform, and you can get the information. Okay, and again, so just like here, if you are not actually in the United States, so you need to actually use the or calibrate the S1 and SS or other factors that are especially related to United States regions. So you need actually to calibrate it with your region. Okay, so this is the thing that I wanted actually put my comment here. This is the difference between ASCE 716 and ASCE 722. Okay, so remember in ASCE 722 you cannot find S1 and SS, FA, FV values. Okay, so you need to use the ASCE hazard tool. So this is the thing. Okay,
okay, so thank you, Dr.
Sorry.
Yeah, any question, Mr. Igwan?
Yes. Prof, the problem is that the ASCE, as you said, now, when we refer to their site, it was mostly about America. For countries like Afghanistan, we don't have any code how to check ACEs, AC1 and ACAs.
Yeah, for that one, as I told you, so you need to calibrate, okay? So maybe, you see, we have the MCE and also we have the DBE, okay? So Amr, could you go back to that, response spectrum acceleration for MCE and DBE? Yeah, here, okay? So every country actually, has this response spectrum, okay? For example, for Malaysia also, you have the MCE and also based on MCE, you can calculate the DBE as well. Okay, so you need to go to the seismic map of that particular region, okay, and find the maximum considered earthquake. Okay, so the value, and then so you can actually, let's say, just multiply by the G. And then so according to that, so you can follow the other steps that you have in ASCE, okay, to get the, let's say, other factors. Okay, maybe in this case, I need actually, to prepare something to guide you how you can actually, calibrate the S1, SS, and let's say, other factors that you cannot find it in ASCE, let's say, collections. And you can calibrate it, for your particular site. Okay, so for that one, I will try to prepare something for you to make you understand how you can use the S1 and SS.
Okay, thank you.
Okay, shall I continue?
Yes, please.
Okay, so we have SS and S1 that giving from the Dubai code, and we will use it on this example. As we said, we will go to site classification. We have our shear velocity. This is usually given in the geotechnical report, and there is a table 23.1 that show us based on the average shear velocity, what we should select or what is site class is. So we have in this example 2000 feet per second. So to locate here, and our site class, it will be C, very dense soil and soft rock. And after that, we can calculate SD1 and SDS. But before, we should have FV and FA. FA is when we multiply it with SS, we will have SMS, and FV, when we multiply it with S1, we will have SM1. So this is aiding coefficient for the site class in our structure. So we have site class C, and we have S1 approximately 0.2, 0.18. We will take this value 1.5, and for FA, we have SS approximately 0.5 and site class C, so it's 1.3. As we see here, it's amplified the spectral acceleration. So we calculate SM1 as following and SMS, and then this is the maximum considered earthquake. But we said before we will go for design burst earthquake, so we take 2/3. For SD1, it's 2/3 of SM1, and for SDS, it's 2/3 of SMS. So we will have SD1 as 0.18 and SDS 0.442. Actually, in ASCE 716, these values is given calculated by default in ETABS, but as Dr. said, we use ASCE 722. We should provide SD1 and SDS for the software. But if we talk about ASCE 716, we only provide S1 and SS, and it will do this calculation manually and actually automatically, sorry. And we provide it with site class also. But it's important to do this actually manually because it's related to the other steps. So I believe that every engineer, when have a specific structure, should compute them manually before it's go for software. Then we should go for seismic design category. Actually, seismic design category is very important to guide us what structure system that should we use. Sorry. For the because we have 2 points, as the doctor said, we have two tables, one for SD1 and one for SDS. So table 1162 and table 1161 is related to this. We should know what SD1 and SDS. This is why I said we should compute these values manually before. And we know what our risk category is. In this case, our risk category is 2, and the SD1 is 0.18. It's located here. So our risk category is C. And for the SDS, also the risk category is same for the it's 2, and the SDS is 0.442. It's located also C. There is some cases that we will have a different category for SD1 and SDS. Like maybe if we have C here and D here, what we should choose? Actually, ASCE said that we should choose the most dangerous one. So in the case of having C and D, we will choose D because it will be more critical case. But here in this example, we have same risk category for the two. Then we should select the response modification factor and deflection amplification factor and overstrength. This going to the table 12.2.1. And we see that our plan is, it doesn't have shear wall. So we should go for moment resisting frame system. And why we compute seismic design category? We say it's guiding us what to choose. So we have this B, C, D, E, F, and we have NL and MP and these values. So NL mean there is no limitation. Like if we choose special reinforced concrete moment frame, we have no limitation. Even if our structure in category E, there is no problem of using special reinforced concrete moment frame. But maybe if we go to intermediate reinforced concrete moment frame, so we see for the B, we can apply this. For C also, like in our structure, we can choose between special and intermediate. It depends on the engineering judgment actually. But in D, it's not applicable. So maybe if our structure in D category, we should go for special reinforced concrete frame. We cannot go for intermediate. And actually, these numbers, it's referred to the height of the structure. Sometimes it's giving limitation for the height of the structure. So we will choose special reinforced concrete moment frame. So this is go for input to ETABS. The response modification coefficient is 8. The overstrength factor is 3. And the deflection amplification factor is 5.5. This is 3 should be given as input for ETABS. And finally, we go for period determination. Actually, period determination, I will show you later in software how to have the model period. But first, let's talk about the one that provided by the code. We said that we have this equation TA equal to CT HN power of X. So CT at X is related to structural system. We said that we have concrete moment resisting the frame system. Actually, this value for feet and this is for meter. But in ETABS, you should, even if you work in meters, you should provide it in feet. So remember this 0.016 because we will use it in the ETABS model. But here in the manual calculation, we will use, of course, the meters value. So 0.0466 and HN, we said it's 5.5 and the X09. We have TA, this 0.549 seconds. But as we said, we compare T from model and T multiply CU. We should compute CU is related to SD1. We said SD1 is 0.18, but we will take it at 0.2. So we will use 1.5 CU as 1.5. So we should have TA for TACU. Now we have it. We have T from model analysis. Okay. To have this, we should go actually for software. Let me use software.